Welcome to the virtual tour of a research group of Svetlana Kilina, which means actually this is my group. So we work on using computational chemistry and applying it to research problems mainly focused on properties of materials. So today I will give you a short introduction to what exactly this means, computational chemistry, and give you some flavor what research work we do in our lab. So our research is focused on computational modeling of light-driven processes in different materials. In particular, we consider two classes of materials: molecular structures, such as conjugated polymers or conducting polymers, and also metal-organic complexes. And I will have a little bit more details about metal-organic complexes in my next slide. This is a work which will be assigned to students who will join our group for the summer research. We also work on nanomaterials, and specifically with semiconducting quantum dots, which are small teeny parts of a semiconductor cut from a semiconducting materials and having really a size of a few nanometers. And carbon nanotubes, which also have a very teeny diameter of not more than 1 nanometer and pretty long lengths. So what are these light-driven processes and why they are needed? First of all, they are needed for different devices, and in particular the devices which we call light-emitting devices, which include as a working element the light-emitting diode, LED. Of course, these devices include different types of lighting, also monitors, TV screens, the screens of our smartphones, and so on. The key processes in these devices include the idea that first we have a material. It should be conducting material. On the right side, here is an example of the conducting polymer in this case, which is connected to the contacts with different charges, plus and minus. As soon as this material is connected to the power, so we're really creating the voltage on the different sides of this molecule, then positive and negative charge start attracting to each other, moving towards each other. When they meet, they annihilate with the creation of electromagnetic wave, means that they emit light. In this device, the electricity is converted to light. There is another class of materials, photovoltaic materials or photovoltaic devices, solar cells in particular, where the processes of interaction between matter and the light is kind of the same as I discussed before, but goes in the opposite way, which means that first we need to shine light, for example, the light from sun, which creates electron-hole pair in the conducting material. Then this electron-hole pair are moving in the opposite direction towards the contacts. So we have free carriers, charge carriers, which means that we creating the electric current. So in these devices, the light is converted to electric current and then can be used as electric power in our houses for usage as we usually use our electric nets, electric power. These processes we study in our research and modeling it with computers. What are the tools we use to model these processes in different materials? First of all our things which we can do can be done remotely. Using high-performance computing clusters, which are located at NDSU at the center with the name CCAST. And you just need to get the account, which any NDSU students or community, North Dakota community, can get this very easily. And you can log in and work with these computers remotely. Of course, you also need to have your laptops or computers at home to remotely connect to the CCAST computers. And this is all our research tools. So your home desk or even sofa or even the bed can be turned very easily to the research lab if you work in our lab. Of course, you need to know how to use some special software. You also need to know a little bit on a Linux operation system, because we use Linux to log in and to run the computational works on a high-performance computing clusters. All this knowledge we will deliver to you over short training for the first week, and you will be ready to work from your homes. So let's consider main steps which we have to do if we are doing materials modeling or materials computational modeling. The first step is creating initial geometry of the system. It should be three-dimensional geometry, chemically correct, also very logical, which we have to start with. Next step, we need to optimize this geometry, which means we need to find this geometry will be changed until we find such a structure that provides a minimal energy for this specific system. As soon as geometry optimization is done, we have now the actual geometry, the geometry at the equilibrium for this specific system, and we can start simulating the electronic structure of this system, which means we will know the energy levels, the splitting between these electronic energy levels of the material, and also we learn where the electron is located, on what part of the molecule we have more electron cloud, electron density located at this or this part of the molecule, or this or that atom. Finally, we can simulate the optical spectra, which means it's absorption spectra or emission spectra of the system, and these spectra can be directly compared to experimental data if they are available. After we're done with all the steps, we can analyze our calculated result to establish the structure-property relationship, which means we will learn that how some small modifications, chemical modification to this molecule, to this system, can change the properties, and for our case, we're interested in the optical properties of the system. So we will learn how to chemically justify the structure to improve the optical properties of the system. Then this information can be used to guide the synthesis of materials with the targeting optical properties. For example, we can provide some guidance how to synthesize materials which will emit in the infrared range of the solar spectrum. And as a last step, we can compare our calculated results with experiment, and if the comparison is reasonable, if they agree, then it means we have a justification that our model, our calculated approach is reasonable, is trustable, and we can use it further for other type of materials. For this, we already have established a collaboration with experimental group of Dr. Sun, Wei-Feng Sun, Professor Wei-Feng Sun from North Dakota State University, and she is doing the experiments with the same molecules, structures, as we do our calculations, and then we can compare directly experiment and theory to see how it works together. Let me now introduce the first step of creating the initial geometry, and I will show you how this initial geometry can be created. First, we need to know the chemical structure of the material we're interested in, and here is an example of a specific molecule and its chemical structure, the scheme of this molecule. Now we need to create a three-dimensional structure. For this, we of course need to know a little bit chemistry, understanding the main properties of aryl rings, 5-member rings, also the angles, sp3 hybridized, sp2 hybridized atoms and their properties from structural point of view. With all this knowledge, using the Gaussian software, this structure can be created. We start with already models, just taking it from the database which are included into this software, and then modify a little bit with putting the atoms which we need, like for example platinum in between the nitrogens, then adding additional double bonded carbon in between the 5-member rings, adding aryl rings, substituting one of hydrogens with oxygen, checking that the bond length between platinum and oxygen is in the right distance, then also check the angles. The molecule is planar, but the top group, and we are done. So here we have now the structure ready to calculate for getting the minimal, for getting the structure which provides the minimal energy for this specific system. And this, of course, will be done not by hand, but using the computational software. And you see, this is the final result, the optimized geometry of this system with the lowest possible energy, as was already calculated by my students. After we know the geometry, there are 4 additional steps which we can go and which we can perform. For example, we can check the potential surface or the potential barrier to see different type of isomers for this specific molecule. With isomers, it means it has the same chemical structure but slightly different geometry. For example, in this case, the aryl ring on the top is changing its dihedral angle with respect to the main plane of the molecule, and rotating this angle, we get an energy either going down or up. So we get in this surface potential, knowing, of course, how much different isomers, what is the energy barrier, what is the energy difference between different types of isomers with dihedral angle like minus 60 degrees versus completely plain structure, 0 angle for the dihedral angle in this case. We also can get the information about the electronic structure, the molecular orbitals, which tell us where the electron cloud, the electron distribution is located, on which specific atoms it's located. So the colors here of these clouds, red stays for the more negative charge, means where the electrons is the most located, and blue where we have less electron density, which means it's more positive part of the molecule. We can do it for different states, occupied, unoccupied. What we call occupied would be holes, unoccupied would be electron. So this information might be useful for knowing the properties of the materials. We can calculate the absorption spectra and also get the information how this excited, now not ground state, but excited state electron-hole pairs contributing to each of this optical transition, where this density is located with respect to the molecule for the different types of the transitions, the first transition, second transitions, and so on. And as a final step, we can compare the calculated absorption spectra with experimental spectra for this molecule. And here I'm showing it's slightly different molecule, actually 4 different molecules with some substituted groups, comparing experimental results from Weifeng group, experimental group, and our computational data. As you see, they are in a very good agreement, which justify that our methodology and the things which we are simulating reasonable and can be used further for the further analysis of these materials and their optical properties. And since this is a virtual tour, I'm showing you how our lab looks like. Here is a working space of one of my students, and showing the software and panels for the things which the student was working on. In this case, it was quantum dots. Here is the room where we have our servers, where we back up all the calculated data. And here is my students, graduate student Jabed and Levi, who are very well experienced with doing all these calculations, and they, of course, are ready to help new members of the group. If you join our group, they will be your first help to ask the question with all technical, all scientific, or research questions. And they are really very nice guys and will be ready to help you. With this, thank you very much for your attention. Welcome to my group. I hope you at least like the idea that everything, the research which we are doing, can be done completely from homes without getting outside from your living space. Bye-bye.